White holes may be the secret ingredient in mysterious dark matter. White holes, which are theoretically the exact opposites of black holes, could constitute a major portion of the mysterious dark matter that's thought to make up most of the matter in the universe, a new study finds. And some of these bizarre white holes may even predate the Big Bang, the researchers said. Black holes possess gravitational pulls so powerful that not even light, the fastest thing in the universe, can escape them. The invisible spherical boundary surrounding the core of a black hole that marks its point of no return is known as its event horizon. Images. Black holes of the universe. A black hole is one prediction of Einstein's theory of general relativity. Another is known as a white hole, which is like a black hole in reverse. Whereas nothing can escape from a black hole's event horizon, nothing can enter a white hole's event horizon. Previous research has suggested that black holes and white holes are connected, with matter and energy falling into a black hole potentially emerging from a white hole either somewhere else in the cosmos or in another universe entirely. In 2014, Carlo Rovelli, a theoretical physicist at Aix-Marseille University in France, and his colleagues suggested that black holes and white holes might be connected in another way. When black holes die, they could become white holes. In the 1970s, theoretical physicist Stephen Hawking calculated that all black holes should evaporate mass by emitting radiation. Black holes that lose more mass than they gain are expected to shrink and ultimately vanish. However, Rovelli and his colleagues suggested that shrinking black holes could not disappear if the fabric of space and time were quantum, that is, made of indivisible quantities known as quanta. Spacetime is quantum in research that seeks to unite general relativity, which can explain the nature of gravity, with quantum mechanics, which can describe the behavior of all the known particles, into a single theory that can explain all the forces of the universe. In the 2014 study, Rovelli and his team suggested that, once a black hole evaporated to a degree where it could not shrink any further because space-time could not be squeezed into anything smaller, the dying black hole would then rebound to form a white hole. Previous research has suggested that black holes and white holes are connected, with matter and energy falling into a black hole potentially emerging from a white hole either somewhere else in the cosmos or in another universe entirely. In 2014, Carlo Rovelli, a theoretical physicist at Aix-Marseille University in France, and his colleagues suggested that black holes and white holes might be connected in another way. When black holes die, they could become white holes. In the 1970s, theoretical physicist Stephen Hawking calculated that all black holes should evaporate mass by emitting radiation. Black holes that lose more mass than they gain are expected to shrink and ultimately vanish. However, Rovelli and his colleagues suggested that shrinking black holes could not disappear if the fabric of space and time were quantum, that is, made of indivisible quantities known as quanta. Spacetime is quantum in research that seeks to unite general relativity, which can explain the nature of gravity, with quantum mechanics, which can describe the behavior of all the known particles, into a single theory that can explain all the forces of the universe. In the 2014 study, Rovelli and his team suggested that, once a black hole evaporated to a degree where it could not shrink any further because space-time could not be squeezed into anything smaller, the dying black hole would then rebound to form a white hole. The local density of dark matter, as suggested by the motion of stars near the Sun, is about 1% the mass of the Sun per cubic parsec, which is about 34.7 cubic light-years. To account for this density with white holes, the scientists calculated that one tiny white hole, much smaller than a proton in about a millionth of a gram, which is equal to about the mass of half an inch of a human hair, Rovelli said, is needed per 2,400 cubic miles, 10,000 cubic kilometers. These white holes would not emit any radiation, and because they are far smaller than a wavelength of light, they would be invisible. If a proton did happen to impact one of these white holes, the white hole would simply bounce away, Rovelli said. They cannot swallow anything. If a black hole were to encounter one of these white holes, the result would be a single larger black hole, he added. As if the idea of invisible, microscopic white holes from the dawn of time were not wild enough, Rovelli and Vidotto further suggested that some white holes in this universe might actually predate the Big Bang. Future research will explore how such white holes from a previous universe might help to explain why time flows only forward in this current universe and not also in reverse, he said. Rovelli and Vidotto detailed their findings online April 11 in a paper submitted to the Gravity Research Foundation's annual contest for essays on gravitation. How does a white hole form? As white holes are hypothesized to be closely related to black holes, there are several theories as to how they might form. The theoretical origins of white holes can be traced back to Russian cosmologist Igor Novikov in 1964. Novikov came up with the idea of white holes as a sort of cosmic twin to black holes as part of a solution to Einstein's field equations, building on the work of German physicist Karl Schwarzschild, who described the spacetime geometry of empty space surrounding any spherical mass. Schwarzschild's solutions to Einstein's field equations included the prediction that if a mass were compressed inside of a critical radius, now called the Schwarzschild radius, then its gravity would become so strong that not even light could escape. In other words, it would become a black hole. But Schwarzschild's description also included the possibility of a theoretical twin for the black hole, as well as what we now call wormholes, folds in spacetime that objects in space can theoretically pass through to near instantaneously cross great distances, in between the event horizons of a black hole and a theoretical, negative version of the singularity. In 1960, mathematician Martin David Kruskal extended Schwarzschild's work to include a reflection of the black hole singularity, but it was Novikov who developed this into the notion of a white hole. Until more recently, physicists treated the possibility of white holes as a mathematical exercise. They could be shown to be mathematically feasible, but were seen as being impossible in real life. One reason for this was that no one could come up with a mechanism for how they would actually form. A black hole is formed when a star collapses, but the reverse of this, a black hole erupting into a star, would seem to violate the laws of entropy. A different theory suggests that white holes aren't twins of black holes, but what happens to a black hole upon its death, albeit for a very, very brief moment. However, the work of physicist Stephen Hawking demonstrated that black holes can in fact emit thermal radiation, Hawking radiation, due to the steady conversion of quantum vacuum fluctuations near the black hole into pairs of particles and antiparticle. The positive particle escapes, while the negative antiparticle falls in, causing the black hole to lose mass. Over time, Hawking radiation reduces the mass and rotational energy of black holes and could theoretically cause a black hole to evaporate. This brings up a number of questions, however. One of which is that, if a black hole can evaporate away, what then happens to the information that it swallowed? According to general relativity, this information can't escape, and according to quantum mechanics, it can't be deleted. The answer, for some theoretical physicists, is that it disappears down a wormhole and emerges from a white hole. Some physicists suggest that once a black hole grows small enough, it could transform into a white hole. This white hole would, TARDIS-like, be minuscule on the outside. But the inside would contain much of the information swallowed by the black hole, which would then emerge over time. Still, others have suggested that the explosion of the Big Bang might in fact have been the emergence of information from a white hole. Do white holes exist? Currently, there's no evidence pointing to the existence of white holes in the universe. As of now, the white hole is a purely theoretical concept. The closest thing we've seen to a potential sighting of a white hole in space came from a paper published in 2011. Scientists speculated that the known gamma-ray burst GRBO 60614 may be the remnants of a white hole. Aside from that, everything we've seen written on white holes is purely theoretical. Despite this, there's hope by some in the scientific community that the existence of white holes will be proven eventually. After all, Einstein published his general theory of relativity in 1915, which predicted the existence of black holes, but it was 1971 before the first black hole was actually identified. While many scientists view white holes as a purely mathematical exercise, others are hopeful that we'll be able to spot this markedly rare astrological event eventually. Although, we may not recognize it when we do. Stephen Hawking pointed out that white holes and black holes could behave in an identical manner, making them virtually indistinguishable. Much of the uncertainty with white holes comes from our current understanding of astrophysics. White holes are, by nature, thought to be incredibly unstable. There's no way a cosmic event expelling that much matter could sustain itself long enough to be caught in an astronomer's telescope. Some speculate that when white holes begin to expel matter, once the expelled matter collides with any matter in orbit, the system would immediately collapse into a black hole, possibly creating an infinite loop of white holes turning into black holes and vice versa. White hole gravity. Much like how what goes on at the center of a black hole's singularity requires one to stretch their understanding of classical gravity, white holes may also need to be looked at through a special theoretical lens in order to be proven. The closest thing to this we've seen is the idea of loop quantum gravity, currently a far-out theory on the fringes of mainstream physics. According to this theory, spacetime, The fundamental concept of Einstein's groundbreaking work on relativity is made up of a series of loops, at their fundamental level tying everything together in a never-ending network of nodes. These loops tie together space, understood as blocks under this theory, and could prevent dying stars from collapsing into points of infinite density, instead recoiling and turning into white holes. Should the approach of loop quantum gravity to white holes be demonstrated as possible, then many of the supernovae astronomers have observed over the years could turn out to be markers of a white hole's formation and death, much like some of the theories around GRBO 60614.